Hi everyone. This is my final project for ADTA 5550. I'm Parker Lackland, and this is the project for image classification on the CFAR 10 dataset using convolutional neural network. So this project had the goal of implementing a convolutional neural network on this specific dataset and then comparing the model to the homework for CNN that was implemented and how we can possibly improve on improve on the convolutional neural network model from our homework for. Um, again, the goal was to implement and improve on the convolutional neural network model for the CFAR 10 classification problem specifically. The CFAR 10 dataset consists of a bunch of images, and each image could be classified as one of 10 different objects or labels that we'll go into a little bit later. Just a little bit of an overview of the dataset. The CFAR 10 dataset consists of 60,000 images total, with 10 classes that could be classified on. The training distribution consists of 50,000 different images, while the testing distribution consisted of 10,000 different images, which is pretty standard. Again, this is a classification problem. So images were provided to us for the purpose of classifying them as certain labels that were also given to us in the data. And these labels consisted of whether it was an airplane, an automobile, a bird, a cat, a deer, a dog, a frog, a horse, a ship, or a truck. Again, a little bit later, when we visualize some of the images, you'll see that the images were not perfect. They were quite pixelated and blurry, and it wouldn't be completely easy to classify on these objects, even for the human eye, let alone for a deep learning algorithm. But with some accuracy, you would be able to classify on these, especially some of the ones that would be easier for humans. The data pre-processing was mostly given to us, but the code that was given to us showed that the data files were zipped together. They had labels that were added to them eventually from another data file, and some of these images were visualized so that we could see kind of what they looked like and kind of how they would fit into our algorithm. And then one hot encoding was also performed, so that the data shape would fit well into our model initially. So we were first asked to provide a model architecture that was similar to the homework for our um, homework, midterm homework for the class. This model was built using TensorFlow. No Keras was used. We were asked not to use Keras as well. So it was all TensorFlow code used directly in our model and our algorithm. There were two convolutional layers used with 5 by 5 filters and ReLU activation. We'll go more into depth about that a little later. There were two max pooling layers used as well that used 2 by 2 pooling to help reduce some of the spatial size of the matrices that we would be performing computations on. There was our first fully connected layer and a dropout layer in between that would drop out 50% of that output at random. And then our final fully connected layer that also consisted of an output layer that used softmax activation algorithm to um, compute our cross entropy loss, which was also a part of our optimizer, which was Atom, that was used for this certain convolutional neural network. There are other optimizers that you could use that might be more effective for different situations. You just kind of have to decide on a name by name basis for whatever your model requires. But um, by default, the optimizer that is used is Atom for our specific situation, and it definitely worked well for the MNIST data set. So we'll get into how that might be tweaked in different situations. So during model training, we were asked to use 5,000 steps. During the model training, we were asked not to use epochs as well. The steps just tell you how many times a batch of data is fed in to the network and how many revolutions that it's trained in. The batch size was also 100, meaning 100 images at a time were set through these steps. The accuracy of the initial model with two convolutional layers, two max pooling layers, a fully connected layer, or two fully connected layers with an output layer and a dropout layer. This model architecture basically resulted in a an accuracy level of about 70%. Started at 10%, the first 100 steps are about that way anyways, and it grew to about 68, 69, 70% by the 4,000th step or so. Throughout training, the amount of loss decreased drastically, and the accuracy started to plateau around 4,000, 4,100 steps, as expected. Now, the MNIST model was quite different. It resulted in about a 99% accuracy rate, which is very, very accurate. Might be prone to overfitting if you think about it. Some things might need to be tweaked so that the model is not overfit and it would perform well on new data if necessary. But for this case, for homework 4, it worked very well. It was very accurate. The key differences between the data sets is that the CFAR 10 data set was much more complex, had a much higher complexity. There were more data points overall, and the images were also colored rather than grayscale, meaning that the images had more dimensions, a greater depth. They used red, green, and blue colors in the for the input for the classification algorithm. So definitely a higher complexity for the type of data that was used. Again, the MNIST dataset used only grayscale digits. They weren't images that consisted of a car or a truck or something that would require greater brain power to classify, even by the human eye. So a simpler convolutional network like this would be optimized better for the MNIST data set overall. A two convolutional layer, two max pooling layers, and two fully connected layers would work fairly well for a simple data set like the MNIST data set. So to improve on our initial model, there are plenty of things that you could do. There are plenty of options that could be used to improve on the model's accuracy. Some options would be to increase the depth of the model overall. You could add some layers in. You could increase the number of filters. You could increase the number of steps. I'll explain a little bit what that means. Adding adding another convolutional layer and adding other pooling layers would add to the depth and would add to the complexity of the model, meaning that it would be able to extract some more complex features than a less complex model would be able to, if that makes sense. Um, Also increasing the number of filters would do a similar thing. It would add to the model's complexity. And then increasing the steps during training of the model would basically just allow the model to be trained longer so that if the accuracy continued to increase and never plateaued during training, it would continue to increase and increase and increase. You could see the model's true accuracy rather than the accuracy that's given in the steps before it plateaus. So for the proposal for my model's improvement would be to add another convolutional layer So three convolutional layers in total, add another pooling layer, again, three pooling layers in total, and then increase the number of filters from 5 by 5 to 7 by 7 filters, and increase the number of steps to from 5,000 steps to 7,000 steps during training. So after these modifications were made to the model design, um, the accuracy metrics showed that it started again at about 10% around the first 100 steps. It improved to similarly about 68%, maybe a little bit less, plateaued around the same steps, so 4,000 or 4,100 steps. Again, 7,000 steps were used, so it shows that the increase in steps didn't really help the overall accuracy of the model at all. Plateaued around the same space, meaning that it trained for about as long as it needed to train in the first place. Some of the challenges for redesigning this model were that the extra layers, the greater filter size, and the increased amount of steps had little to no effect on the model accuracy overall. So we'll get into a little bit of that as we go in and we look at some of the code. So here's where we go into a little bit more of the code. The first notebook that I will be going through is the initial model implementation, a similar model to the model that we used in the midterm homework file. We'll go through the data loading and pre-processing procedures, the architecture of the model, which we kind of brushed up on already, and the definition of this model's architecture. And then finally, the training and the evaluation of the model overall. And then the second notebook that we'll go through, which is also another Jupyter notebook file, will be the redesigned model with the added convolutional layer, the added pooling layers, the hyperparameters that are tuned, and the training and testing of this model. And finally, we'll go through and compare. We'll be comparing the two models the whole way through, but we'll go through and compare how the changes in the architecture of the model and the parameters of the model helped or did not help the accuracy of the model of the two separate models. This is the first notebook that I will be sharing. It consists of the initial model architecture that was used that's similar to our homework 4 model architecture. Here you see all of the data pre-processing that was pretty much given to us. The data was loaded here. It was separated into different batches, which it was already separated into. All of these batches were then zipped together, and the labels were added to the data. Here you can see all the different classes, the automobile, the bird, the cat, the deer, all the 10 different classes that were used for classification during our deep learning algorithm. And then several of the images were displayed, for example. You can see here this first one would not be particularly easy even to the human eye to classify what that might be, which leads you to believe why it might be a little bit harder for that deep learning algorithm. I have no idea what that thing is. So it would be a little bit difficult for this convolutional neural network with simple, not a whole lot of depth to classify what that is. But just that's jumping ahead a little bit. These are just some different examples of what the images look like. So here you see that's pretty simple. That might be a bus or something in a car, but just some examples. Then the functions were created to help rearrange some of the data and reshape it. One hot encoding was performed so that it showed the presence of the different labels or the different input variables so that they could be fed into a mathematical algorithm rather than being used just as words or classification. Python doesn't handle that very well. So they had to be one hot encoded, and they were. And then this image data was set up to be ready to be fed into our first convolutional layer. Some of the dimensions were tweaked. Different things were set up. The picture was a 3 by 32 or 32 by 32 by 3 picture had those dimensions. These images were set up perfectly so that we could already feed them into our first convolutional layer and we wouldn't have to worry about any of the data preprocessing. So most of that code was given to us, and we move on to the actual architecture of our model. Here the functions were created the supporting functions were created to build, train, and test our initial model. First, the weights of our filters were initialized here, the standard deviation of 10% of 0.1. Then the bias was initialized. Again, we have about a 10% bias included in our equation. The first convolutional layer was then set up, and the computation for our convolutional layers in general is the input times the weights. And the algorithm figures out the weights for us a lot, which is part of the deep learning aspect of things. But you can see here that that we used a stride of 1 and padding of the same, meaning that there's just a layer of padding around, ensuring that there's some room for error in our algorithm. Then you see that we set up a ReLU layer. The ReLU activation function is used for our model. And then the dot product would be computed off of that. We set up pooling layers to help reduce some of the spatial size, which we'll get more into a little bit later. You can see that the strides were used also, a stride of 1 and padding of the same. These are the same hyperparameters that we tuned before. And you can also see that the max pooling layers that we used use a kernel size of 2 by 2, which just helps reduce that spatial size by about half of our matrices that we're using in our algorithms. Then you see the function for setting up our fully connected layer and performing these computations for the fully connected layer. Here is where the bias is first initialized for our algorithm. It is initialized here. Here's where the bias is first initialized. Then we move on to actually building the architecture of our initial neural network. TensorFlow is used explicitly. There is no Keras used as a byproduct of TensorFlow. It is just TensorFlow code used directly in the project. Placeholders were created with a float data type. Here you see the dimensions of the input, which is 32 by 32 by 3. You know, again, that the 3 is the depth of the actual input, which is that red, green, blue hue that you see in the pictures rather than just grayscale digits like we see in the MNIST data. And then you see this yTrue placeholder is created also as a float data type, and it shows those 10 possible classes that we are classifying those images based on. Again, none of the data is required to be reshaped like it was in the MNIST data set. All that reshaping was done for us in the initial data preprocessing code that we were given. So no additional reshaping is necessary. So we move on to creating the first convolutional layer and the ReLU layer that's associated with it. Again, those computations for the first convolutional layer would be the inputs times the weights. This is the first computation that is used in that convolutional neural network algorithm. You can see that the first convolutional layer is created in this model with a 5 by 5 filter with 3 input channels, which is that red, green, blue hue, that red, green, blue input rather than grayscale, and 32 output channels. We create that first layer. You can see here the dimensions in the first layer. It's again used for the outputs. Then there's a pooling layer that's created. That's the next step. This helps reduce the spatial size in half. Then the second convolutional layer. Now here the dimensions double. The filter size stays the same. The input channels then are the output channels of the previous convolutional layer, which would be 32. And the number of output channels would then be 64. And here you can see the filter size again. the input size and the output size, 32 by 64. Same thing, we add another pooling layer, which is another 2 by 2 pooling layer. This helps reduce the spatial size in half. Finally, since this is just a two convolutional, two max pooling layer architecture for our convolutional neural network, we then flatten the data from the final pooling layer to ensure that it's ready to be fed into the first fully connected layer. Here you can see that these dimensions would be 8 by 8 by 64, which is the output of the final pooling layer. Then we finally create our first fully connected layer, and we apply that ReLU activation function, which is very common to this layer. Then we output this data to the dropout layer, which we'll talk about in just a second. It is right here. The dropout layer then would be set up to drop out a given amount of randomly selected outputs from that first fully connected layer. Then the final fully connected layer is completed and it produces the final outputs. And you can see here that the output size is 10, which is the amount of classes that we have in the data set. These would produce the final classifications of each of the images in a binary format, as we one-hot encoded the variables earlier. The loss function that we created is, again, the softmax cross entropy loss function. And the optimizer that was used, that's very standard for simple convolutional neural networks, is the Atom optimizer with a learning rate of 0.001. Then the trainer is created so that we can train the model in a further step. Now, phase 2 is the actual training and testing of the model that we've created the functions for. Now, the variables are initialized. The steps have been set to 5,000, which was asked of us in our initial model architecture. And then the final training session is run. And first of all, we store these accuracy results in an array. There's a blank array to start with. We run this TensorFlow session with a batch size of 100, as we spoke of before. There's 100 images in each of these training sets, and the batch size is looped through, so throughout training. The trainer is run for each of these batches with a hold probability here, which is our dropout rate of 50%, meaning that 50% of the output of the first fully connected layer is dropped out at random, and the remaining 50% is added to the second fully connected layer, which produces our final outputs. Just helps you get a randomized version of your outputs so that you can eliminate some of the bias in the equation for our algorithm. Then you see here the actual testing of our algorithm. You can see that the predictions from our training are compared to the actual matches. And you can see here also that the test images were used rather than the training images from the data set. And the hold probability here is 1 because we want to keep all of those testing images for the purpose of testing the accuracy of our testing the accuracy of our actual trained model. So we'll go into this in a little bit more depth, but you can see how at step 0, the accuracy is about 10%, and then immediately it jumps to about 32. It continues to train well. It learns through step 1000, still learning, plateaus a little bit through about 1500, 2000, but we're still growing 64%, 65%. We get all the way here to about 4100, and you start to see about the 70% range, which is where we generally end up. It hops up and down, but we're at 69, 69, 70%, 69%. Our final step calculates just below 70% at about a rounded out 69%. So 70% is about where the model plateaus and are for all accuracy purposes. Here's just the collected accuracy data. We put it into a pandas data frame. You can just see it a little bit more linearly, how through the 5,000 different steps, you can see how it grows from about 10% to about 70%. So again, that's our initial model architecture, and that's the code walkthrough for our first Jupyter notebook. This is the second Jupyter notebook that we'll be discussing. It is discussing the model redesign. In our previous video, we discussed the architecture of our initial design in a little bit of depth. This will discuss how we improved on or attempted to improve how I am attempted to improve on the design, the architecture of the model, and whether or not it improved the accuracy of our convolutional neural network overall. So here, the beginning of this is again just the same data pre-processing that was given to us in the initial model. All the files were zipped together, concatenated. The images were displayed the same as before. One hot encoding was performed the same as before to show the 10 possible labels and the presence or the lack of presence of those labels. The image data was set up to be fed perfectly into our fully connected layer, and then the images are set up by our CFAR helper. The same functions were set up and initialized to help build, train, and test our CNN model. The weights for each filter were initialized, the bias was initialized, the convolutional layers, the ReLU layer, which is the activation function, again, to help perform our dot product computation. Then the pooling layers were created to help reduce the spatial size, and the fully connected layers were used to help finish that computation and add the bias to the equation during our algorithm. So for our redesigned project, we built another convolutional neural network. Placeholders were the same dimensions of the input, same number of classes. It's based on the same data, so no reshaping was necessary again because of the previous code that we were given to help with our data pre-processing for this algorithm. So again, the first convolutional layer was created with a ReLU activation function. The filters were changed just a little bit. We increased the number of filters in hopes to increase the complexity of our algorithm. So the filters went from a 5x5 filter to a 7x7 filter. The number of strides were the same and the padding were the same. So there's a layer of padding around that 7x7 filter. It's just a little bit more complex than our last design. The filter shape you see here is 7x7. The same amount of input channels were used for red, green, blue, and the same amount of output channels were used. Then the first pooling layer was created. We used the same amount of max pooling, 2x2. It's the same exact thing. A second convolutional layer was created. The number of input channels here is the same as the last second convolutional layer, which is 32. And the number of output channels is the same, which is 64. The filter size is still 7x7. Just like our first convolutional layer, not quite like our first convolutional layer of our previous model. 7x7, 32 input channels, 64 output channels. The second pooling layer was created to reduce that spatial size again. And then finally, we increased the depth of our initial model by adding a third convolutional layer and performing the computations in this layer. Here you see that the dimensionality of the outputs changes again by double. The number of input channels is the number of output channels of our previous convolutional layer, which is 64, and the number of output channels would be 128 by then. Same filter size, 7x7 again. That final pooling layer is created to be fed into our first fully connected layer. It's reshaped. It has dimensions of 4x4 by 128 at this point. When our first fully connected layer is created, our dropout layer stays the same. It's about 50% dropout at random. It's the same exact function created, same exact idea of design, rather as opposed to us creating another convolutional layer to add to our design. The output size here for our final fully connected layer is still the same. It's 10 because that's the number of classes that we can possibly classify an image as. Loss function is the same. Optimizer is the same. You could experiment with other optimizers. I thought about it initially. It depends on the situation. And the Atom optimizer is a default optimizer for our TensorFlow code, but it's possible that another optimizer could optimize some of the performance a little better. So maybe use a different optimizer in different situations. We did not do this for the current redesign, but it's just another option for the future. So as we train this model, again, the variables are initialized. We increased the amount of steps here to 7,000 in hopes that the 5,000 original steps did not train our model completely. I thought initially that it probably did because our accuracy results plateaued around step 4,000. But maybe the model would continue to train until step 7,000 or later, and we would find higher accuracy values. So maybe it just needed to be trained a little longer. So we increased that number to 7,000 instead of 5,000. Then we ran the same session with the same batch size of 100 images about um, the same dropout rate of 50% at random, and the model was trained. The matches were compared, and the model was tested on the testing data. We ended up seeing very similar results. You see here we have the same on step 0, about 10%, a little bit greater accuracy initially, not much though. It's not comparable really. Um, and then we gradually increase to around 55%. The increase is slightly more gradual and then plateaus around the same step. Around 4,500 or so, we get to the 65, 66 range, get a little bit to the 67 range around 6,800, but the accuracy really levels out at about 66% by the end of everything, which is slightly less accurate actually after adding that final convolutional layer and final max pooling layer, increasing the amount of filters and increasing the amount of steps during training. So the accuracy stays about the same, honestly, a little bit less, which confused me a little bit, but there are further things that you could do to research how to further optimize an algorithm like the convolutional neural network. So here again, we just put those accuracy metrics into a pandas data frame, and it shows you that you're about at that 68, 67, 66% range for our accuracy. So I will go back now to our PowerPoint presentation and finish up. Here we are again. We've gone through the code walkthrough now. You can see that the redesigned model didn't change the accuracy drastically. It honestly did not improve on the model at all. There are many different things that could have been done to help improve on this accuracy. Just the things that I did not necessarily improve on that accuracy initially. So there's further research to be done. So the lessons learned, the importance of CNN architecture tuning is great. There is a lot of experimentation that needs to be done to improve on these deep learning model accuracies. Initially, you can think one thing, and then by the end of the day, after a lot of experimentation with the different um, hyperparameters that you could tune and the different depths of every model, every data set's different, and you can improve based on its complexity. You can improve on that accuracy greatly by changing the depth, by changing hyperparameters, by standardizing your data. You can do all kinds of things that change the metrics for your model. So the importance of experimenting with the architecture and experimenting with these hyperparameters is great. For the future, again, just trying different architectures. I didn't standardize the data or normalize the data. That wasn't done in the data pre-processing either. I think that would probably help pretty greatly because it would eliminate some of the noise and some of the extracurriculars going on with the data. That would probably help with the model's accuracy as well. And then just maybe using some hyperparameter tuning functions such as grid search, whether you're manually searching, using grid search, you're using Bayesian statistics to help you through some of these different tuning techniques, but any of these things will help you to optimize your model fully. I'm quite positive that 70% is on the low end of how accurate that convolutional neural network could be for that CFAR10 data set. It's not the biggest data set in the world, and it could definitely be improved upon. So, in conclusion, I successfully implemented a convolutional neural network model for the CFAR10 dataset. The model was then compared to that initial MNIST CNN model from Homework 4. I experimented with some of the model design, whether it was architecture, hyperparameter tuning, and tried to improve upon that model. It was eventually decided that further optimizations and further research would be necessary to find higher accuracy rates for that model. So that's all I've got for this presentation. It was a pleasure going through all of it and learning about all of it. I appreciate whoever's listening, and thank you